Yeah, thank you for the introduction, and thanks Auntie and Sasha for giving me this opportunity to speak here. Today I'm going to talk about the dimension of self-affine measures when the linear paths of the maps in the FS are diagonal. Let us first recall what are self-affine fractals. They are generated by a fine iterative function system, by which we mean a finite family of invertible contracting affine maps. Here, AI are called linear paths and TI are called translation paths. For each such IFS, we can find a unique non-empty compact set on RD such that K coincides with the union of its images under the affine maps in the FS. So we call it a self-affine set. From another point of view, this K is also the set of limit points of the orbit starting from any point driven by the semigroup generated by the maps in the FS. So we can also call it a limit set. If we are further given a probability vector P, with Pi as weights, then we can find the unique Borel probability measure mu on RD, such as mu equals the P weighted sum of its images, affine images under the maps in the FS. So we call it a self-affine measure. If you like a random walk, this mu is also the unique station measure of the random walk that at each point x goes to phi I of x with probability Pi. So this uniqueness follows from the contracting nature of the maps. And in particular, we call this K and mu self-similar when these maps are similarities. That is, the linear paths are multiples of orthogonal matrices. And we call K and mu diagonal if the the linear paths are diagonal matrices. And here are two examples of self-affine fractals. The first is the Bus-Lane Feng. And the linear paths are not all diagonal. And the second is the Hiranaga curve. And here the diagonal paths are all, the linear paths are all diagonal. Actually, what we are seeing, they are not self-affine set, but the self-affine measures because they are plotted using the method of chaos games in the book of Faulkner. So since I put more weights, for example, in this curve, I put more weights on the maps in the bottom, so we see a darker color in the lower below and a lighter color in the above. So this is two examples. Our basic fundamental question is to determine how large are these self-affine set K and the self-affine measure mu in terms of the dimensions, because we are in fractal geometry. And which dimensions we care about? For this self-affine set K, we care about the most famous one. This is a Hausdorff dimension. And for this self-affine measure mu, we care about the so-called exact dimension. This dimension defined to be the constant dim mu, such that if you look at the mu typical point x, then you will see the measure of this small ball centered at x will decreasing when the radius r goes to 0, and this limit exists and is constant at a typical point. So any measure with this property is called as exact dimensionality, exact dimensional measure, and the exact dimensionality for self-affine measure has been progressively established by Zhou Feng and Hu in the diagonal case, and then Barami and Kemeti when the Neapel spectrum is simple, and finally in full generality was due to Zhou Feng. One biggest advantage of this exact dimension is that many common use the notions of dimensions for measures, they coincide. In particular, we can use entropy to detect the uniformness or the size of this measure. And there are some lateral upper bounds for these dimensions, geometrical dimensions in RD, this Hausdorff dimension and the exact dimension. They are defined using the singularity function of Faulkner. These singularity functions are nothing but the products of singular values in a decreasing order. And the famous affinity dimension denoted by dim A of phi is due to Faulkner is defined to be the unique zero of this family of topological pressure. And there's an analog version of this affinity dimension is the Lyapunov dimension for this self-affine measure is called a Lyapunov dimension is defined to be the zero of this equation. This is the so-called entropy. This is the Lyapunov exponent. And because of the nature of this decreasing order, this somehow this T and this Lyapunov dimension gives you the best way to consume this entropy. If this is your first time to see affinity dimension and the Lyapunov dimension, you just remember 3 points, then we can proceed. First, they are analogs of the similarity dimensions. For example, log 2 or log 3 for meters of the content set. And third, they are independent of the translation part. You can see of these equations, there's no translations. And the third is that they are lateral upper bound, respectively, of the whole of dimension and the exact dimension, or just dimension of this mu. Now we can make a quick summary of the relations of dimensions. So in the geometrical space in RD, we have the dimension of measure and the host dimension of K. Since measure is supportive of K, there's this inequality holds and they stay in the RD, so there's another trivial upper bound D. And we can define the natural coding map from the symbolic space. This lambda to the power n, this lambda is the alphabet we got given to the fs, is finite, and we can define this coding map is the orbit. If you are given a sequence or choice of maps, then this is just a limit of this iteration of the starting from 0. And this is independent of the starting point, and the limit exists because of the contracting nature. And as we can see, the upper dimension is bounded above of this dimension of mu, and the affinity dimension bounded of the host dimension. And we can temporarily to refer the dimension in RD as the geometric dimension, and the dimension lives in the symbolic space, the symbolic dimensions. So symbolic dimension bound the geometric dimensions. And we can see there's another row, and we will quickly see why I draw this additional row. And much research nowadays, they aim to show the inequalities in this diagram in various settings, typically or specifically. For example, in this first row is in the symbolic space. This equality belongs to the topic of thermodynamic formula for sub-additive potential. So to achieve these kind of goals, there are several major difficulties. The first is the overlaps, which roughly speaking the support of mu under the maps, they overlap each other, which makes it difficult to estimate the measure of both. And we will see this phenomenon just in the next page by examples. And also the second equality is the non-conformality. This only happens in higher dimension, which roughly means both are mapped to the ellipsoid. Then the natural covered by cylinders, they are not efficient, and also different direction, you have different contraction rate, and because of this non-conformality, you will see from the Larape-Young formula, which is a theoretical formula for the dimension of the original measure mu, and you will see that the dimension of the original measure mu will depending on some some projections of this mu. So and along the oscillated directions. So this is why I draw the additional row here. Because in non-conformity, we have to consider the projections. And the third phenomenon is so-called saturation, which roughly means some part of a measure or set are trapped in some subspace or curves. You don't know how much they're trapped in these subshapes. So this phenomenon is so wide. So people just want to assume some no saturation condition. For example, irreducibility to destroy this phenomenon. So actually, we will also see one example of this saturation later. So now we will see the example for overlaps. So let us focus on the very simple example on the line. So there's no there's no conformality and no saturation or trivial saturation. And then we only consider a system of two maps that have the same concentration ratio lambda, and we give it the equal weight half and half. If this lambda is 1/3, then we get the famous Cantor-Lebesgue measure. Then we can compute the dimensions log 2 over log 3, because if you look at a small ball, you know from the Birkhoff ergodic theorem, the decreasing rate of this cylinder is log 3, and then you know from Shannon-McMillan Bremen theorem, you know the mass of these cylinders is decreasing with rate of log 2. So, and you know this is separated. So you look at the balls, there's only one cylinder in the ball, so you know this is the decreasing rate is log 2, log 3. Log 2 is entropy, log 3 is the Lyapunov exponent. But however, if we increase the contraction ratio to beyond 1/2, then we will see overlaps during the iterations. For example, if you want to then this is called a famous Bernoulli convolutions. If you look at you want to estimate the measure of balls, like here, then you want this small ball, then you want to count how many cylinders here you can estimate the measure, but it overlaps and make it really difficult to estimate because you don't know how many cylinders here. So this is why it's difficult to estimate dimension of Bernoulli convolutions. And there's a Faulkner conjecture in our community. It's called the exact overlap conjecture, which says for any fs, affine fs on R, if it generates a free semi-group, which means you iterate along different words, you get different maps. Or geometrically, here means this phenomenon, two cylinders do not exactly overlap each other, these blue rectangles. So if this exact overlap phenomenon doesn't happen, then you have this dimension of mu attempts natural upper bound, which is the minimum of the dimension of ambient space and the Lyapunov dimension. And there's a version of this conjecture for self-similar set was due to Karoshima in 1996. So this is the exact overlap conjecture. Now let us focus on what is our research target. So classical result of Faulkner, Solomiak, Jordan, Polygon-Simon, they said if we assume some sharp norm condition, then we will see at the big almost all translations, the dimension of self-affine set and dimension of self-affine measure, they attain the natural upper bounds respectively. And since the pioneer work of Faulkner, there's an amount of progress to understand these typical self-affine fractals. And this kind of result refute the generic phenomenon that give you the rough idea what should be typically behave. And sometimes will give you will prove the existence of some new phenomenon. This is very interesting from this perspective. And now we move to a related but a little bit different direction, which is we want some explicit examples such that this equality 1 hold, and we want the more the better. So this question motivates our research target to find checkable and mild conditions for this equality 1 to hold. And the exact overlap conjecture in the previous slides is within this topic. Now next we introduce some progress towards this research target. For this kind of research target, we cannot avoid the famous breakthrough of Mike Hockman, which relies on this kind of so-called exponential separation. So this separation are defined in as follows. So we can define this distance between any two affine maps on the R, such that if the contraction ratio are different, we define this just to be infinity. If their contraction ratio is the same, then we define the distance of them to be the difference of the absolute value of difference of the translations. In particular, if this is 0, then these two maps coincide. Then we can define the separation of this affine Fs on R to at a scale n, to be the minimum distance of two affine maps iterated along two different walls. And this is the minimum distance of these two different along the maps along two different walls of the same length. n. Then we define this affine fs. This fs is on the real line to be if exponentially separated. If we can find a very, very small c such that at infinite many scale, the separation of this fs is lower bounded by this c to the power n. So this is called exponential separation. For this separation condition, we have two remarks. The first is that we can check that this holds. When this holds, for example, is phi, if this fs phi is defined by algebraic numbers and there's no exact overlaps, then this phi satisfies this exponential separation. And also, this is a separation condition is extremely mild, and it allows substantial overlaps, and they are mild in the sense that if we are given a parametric family of fs on the very, very mild assumption of regularity or transversality, then the exceptions are really, really small in packing dimension or even. So I hope these two remarks can convince you that the exponential separation is a good candidate for our research target. So now we are ready to introduce the famous result of Hockman. Firstly, he proved that on the real line, if the IFS is exponential separated, then for self-similar measure, attempt the corresponding self-similar measure, the dimension of it will attempt the natural upper bound, and I denote this equation as m. M means measure, and then if we choose a the special weight, then you will probability weight, then you will get the corresponding result for the self-similar set. This attempt the natural upper bound. So I denote this equation as S, which means the set. And there's also some progress towards the exact overlap conjecture on the real line. The first is the Peter Walliu proved this conjecture combined with the result of Hockman for ballooning convolutions. Later, Ariel-Rappaport proved that we can only assume the contraction ratios are algebraic and there's no assumption of on the translations. Later, Rappaport and Zhou made a great progress in the homogeneous IFS of 3 mass, and also they proved the conjecture for homogeneous IFS with rational translations. Recently, in a joint work with Zhou Feng, we adapt the ideas of Raju and Rappaport Raju. We extend their result to the homogeneous IFS with algebraic translations, and there's no assumption on the rational part, the contracting ratios. And there's some further progress. Let us so this is the progress for self-similar case in a real line. And later Hockman proved the analogous result in higher dimension. If you are happy with this exponential separation condition, and you also assume that this no saturation phenomenon happens, then the self-similar fractals will attempt the natural upper bound. And basically, if you are happy with this very good separation condition and know to prevent this wide phenomenon of saturation, then you have a very good understanding of the self-similar dimension of self-similar fractals. Now, next, let us move to the strictly no conformal setting. There's a good amount of progress in when we assume strongly reducible and proximal on the linear path. Actually, here I'm not going to give you the precise definition of this condition. I only remark that these conditions are mild and checkable. So, and the first breakthrough was due to besides the early development of Barani, Farquhar, and Kempton, the major breakthrough was due to Barani, Hockman, and Rappaport. They proved that on the plane, if you assume strongly separation condition for the measure, the self-affine measure will attempt the natural upper bound. Later, Hockman and Rappaport relaxed the strong separation condition to the non-trivial. Just the IFS, the maps do not have a common fixed point, and assume the mild, very good exponential separation condition. And later, Rappaport obtained the result in R3 and assume the strongly separation condition. And I would like to remark that in high dimension, the corresponding result under this mild exponential separation condition are still widely open. And we can see that in subsimilar case, we can just choosing a very good special weight, then you can transfer the result from measure to set. However, in the self-affine case, the corresponding stuff in the symbolic space, they corresponding to the sub-additive thermodynamic function. We have much understanding recently, but we do not have a very, but still in the progress. But so it's not very direct to choose some special weight or something else. Then you need some variation principle to connect the dimension of the dipole dimension of n-step ballooning measures to the affinity dimension to transfer the result for measure to a set. In the plan, this was due to Morse and Schmucking, and in higher dimension was recently obtained by Morse and Surt. Now we move to our present the setting in our talk, which is the linear paths are all diagonal. Actually, this it has longer history, and in the contrast and complement the strongly reducible and proximal case. This has a very long history dating back to 1980s of the Bedford McMullen copies, and there are many progress in this direction due to many mathematicians. But there's one common feature in this situation is that there's no overlaps. And later, there are some overlapping cases has been dealt with by Fraser and Schmucking and Barney Rams Simon. And after this previous result, significant progress has been recently obtained by Rappaport in diagonal FS. Now let us focus on one general diagonal FS, so which means the linear path AI are diagonal matrices. This Ri, J from 1 to D are conjunction ratios, and Ti just any vector in Rd. And we define for each direction J from 1 to T or 1 to D, we define the J's Neapolitan exponent to be the P weighted sum of this minus log this weighted sum of the log of the contractive ratios, and we defined the IFS projected to the J's direction to be this IFS, this phi J, just taking out J's component of the linear part and the J's component of the translation part. Then we have this IFS phi J. This is the IFS on R. So we have defined the exponential separation for this IFS on R. And the breakthrough result of Rapport says that if for any two direction J1 and J2, if for any two different direction, you can find one maps I such that the corresponding contraction ratio are different, and we also assume for every direction the phi j is exponentially separated. Then the dimension of set attempt the natural upper bound. So this is a very is a clean and a strong result, and Rappaport deduced this result from his analog result for diagonal self-affine measures. Under this additional assumption, we call it the one-dimensional subgroup assumption, which says if you can find a vector in Rd, this C vector in Rd, such that for any map I, the corresponding log of taking log of the corresponding contraction ratios, then you get a vector in Rd. They all, for every I, they all stay inside this one-dimensional line. Then this is the condition. So we call it a one-dimensional subgroup because this is just one-dimensional. This log vector stay inside this one dimension. In particular, this condition star holds when the FS is homogeneous, which means all the linear paths are the same. And the argument crucially relies this condition star, and we will discuss later about this condition. And our main result is to remove this condition star, and we obtain the following result, which is our main result, which says for any two direction J1 and J2, if the corresponding Neapolitan exponent are different, which means the the Lyapunov spectrum is simple, and we assume every projected Fij is exponentially separated, then the dimension of the diagonal self-affine measure attain the natural upper bound, which is the minimum of D, the ambient space dimension, and the Lyapunov dimension. Now let us discuss about these two assumptions. For the first assumption, this is the assumption is necessary by the phenomenon of saturation. I promised you what is saturation. For example, so if we consider this self-similar Fs, which means squares are mapped to the squares, we put many squares along a line on this diagonal. This is the template of the first iteration, and then we further iterate. We will see that these many maps were saturated along the diagonals. You increase the number of maps, you are symbolically increase the upper dimension, but geometrically this dimension, this part are saturated, are trapped in this diagonal line. And if you look at the projection along the diagonal, you will see a Cantor set. So which means in this example, the dimension, if you give this equal weights, uniform weights on the maps, the dimension of this self-affine measure is strictly less than 2 because you project a Cantor set, and this fiber part are trapped in the 9. But symbolically, your upper dimension can go beyond 2. So this upper bound is 2, but actually the dimension, geometrical dimension is 2. So this is the obstruction, this saturation we want to destroy. For the second assumption, we expect this second separation condition to be relaxed by the no exact overlap, just like the no exact overlap conjecture. For this direction, recently, Rappaport and Haoji Ren, they generate the result of Waju for ballooning convolution to a higher dimension. This is the one result towards this direction. But when D is equal to 2, this is just the exact overlap conjecture, which is famous and open. So we don't have much more to say about this direction. So I hope these two remarks can convince you that these two assumptions are mine. And now let us look at the applications. The first two applications are classical, even goes back to the paper of Hockman, as we promised in our research target. So we can check in algebraic FS, if there's no exact overlap, then the dimension can be of the measure can be determined. And also, if you are given a parameterized family of FS, then typically with a very small exception, the exception can be small with packing core dimension 1, and these exceptions are explicit in the sense that they are just parameters which do not satisfy the exponential separation condition. This is a little bit different from the transfer method. Now let us to move to the other two applications. Because we have the dimension of measures, it's natural to ask, where do we can find a measure, self-affine measure, to attain the dimension of the self-affine set? So this is the application 3. In some case, we can do that. We can determine the so-called measures of a full dimension, and by combining these results, application 3, with the recent progress for the orthogonal projection of measures, we can obtain some dimension result for the orthogonal projection of the sets. And now we will see a concrete example for these last two applications. Okay, this example is very simple, just in the real line of two maps, and these maps horizontally are contracted by 5/7, and this vertically is 3/5, and the other map just switched the contraction ratios. Then this is the inhomogeneous FS, and we will see the overlaps because 5/7 plus 3/5, they are greater than 1. We will see there's overlaps. Then if we further iteration, then we will see this approximate of the limit self-affine set. And in this case, we can compute the finite dimension is this 1.66 is a solution of this equation, and we can by our result we can determine that exactly two ergodic measure mu1 and mu2 which are self-affine, such the dimension of this mu1 and the mu2 they attain the Hausdorff dimension of k and equals the finite dimension, and this equality was originally due to Ariel Rappaport, and this equality was due to our major result. And similar examples for this no uniqueness of the measures of full dimension was due to Kamaki and Whipple-Nyland for typical self-affine set, and also for Gazoris-Lallet copied the example in this case was due to Julian Baha and Zhou Feng. Now we have an explicit and overlapping case for this no uniqueness of measures of full dimension. By combining the recent result of Alexei Piola, he proved the orthogonal projection of diagonal self-affine measures without any separation condition. It's very clean. Without separation condition, just assume some irrationality assumption, then he can prove that except the major directions, we can prove the dimension of the measures attain the natural upper bound. Now, by combining his result with this result, we can say for this example, for all one-dimensional line, for all lines in the plane, we can say the Hausdorff dimension of the orthogonal projection of this K is equals to 1. So there's no exceptions. And this is basically the story part of this talk. And I'm not sure how many time do I have. How much time?
You're already slightly over.
I'm sorry. Let's just stop here. Sorry. Maybe let's stop here.
If you have one more slide, show it.
I don't want to explore too much time for you. I think I just point out a major point. So major point is how to remove this conditional star. So to answer this question, we goes back to where this conditional star is used. This is used to prove this entropy increase. One important ingredient is to give a uniform lower bound of the component. If we fix a window M, you give a lower bound of this entropy, finite scale entropy. Look at the uniform across scales. You want to get a lower bound. In homogeneous case, you can achieve this by self-affinity and then zoom out. So in homogeneous case, you zoom out of for this small piece, the support have a size comparable to the partition. Then you zoom out, the arrow is you can control by C over M. The M is the length of window, but in homogeneous case, you cannot get this uniformly along each direction. Each direction you get some arrow. You cannot find this kind of partition, such as along each direction, the corresponding small pieces has comparable length with respect to this partition. I think this is the major point. Then we prove some exact dimensionality and the Labarre-Yang formula, and then we establish the entropy increase based on many ideas from the previous results. That's it.